Okay, so get ready for this one. We're diving into a connection today that I certainly didn't see coming at first.
Right. It seems like two totally different worlds.
Exactly.
Yeah.
We're looking at some, well, pretty serious math differentiation and how it connects directly to, what happens when food goes bad on your counter.
Yeah. The sources you shared really highlighted this, a surprising link. It's fascinating.
It really is.
Yeah.
Okay, let's unpack this then. So, based on that material, what we're zeroing in on today is how differentiation, this calculus concept, actually helps us understand food security. Specifically by looking at the rate of microbial growth, how fast those little guys multiply and spoil food.
And that focus on the rate is, well, it's the crucial part, isn't it? That's what the sources really drive home. Differentiation, I mean, fundamentally, it's the math we use to figure out how quickly something's changing right now.
Like a speedometer in a car, sort of?
Exactly like that. That's telling you the rate of change of your position, right?
Yeah.
The speed. So here in this context, we're talking about measuring the instantaneous speed of, say, bacterial growth on that leftover pizza.
Gotcha. And it's not just like theoretical math problems. Your sources make it super clear that if you really want to get a handle on food spoilage, how fast it's actually happening, you need these calculus tools. Differentiation gives you that precision.
Yeah, it lets you look at the speed of the growth, not just the total amount after, say, 3 days.
Did the sources give examples? Like, how does knowing the speed help?
Oh, absolutely. One study you shared looked at temperature. It wasn't just, oh, warmer means more spoilage. Obvious, right?
Right.
But using differentiation on their growth models, they found this like sharp acceleration in the spoilage rate once they hit a certain temperature for a specific food.
Wow, okay.
And knowing that rate, that acceleration point, is way more useful for preventing spoilage than just knowing, it gets bad when it's warm.
So it's the speed it gets bad at, not just that it does get bad. So why is that specific measure, the rate, so vital for food security overall? What was the connection there in the material?
Well, the sources linked it directly to things like predicting shelf life much more accurately. If you know the rate is high under certain conditions,
you know it'll go bad faster.
Precisely. Faster spoilage rates mean more food waste, right? And that's huge. Food waste hits availability, it hits cost, and ultimately it impacts food security on a big scale.
Okay, that makes total sense.
So understanding how fast things are going south, which differentiation helps us quantify, lets researchers, manufacturers, maybe even us, predict better and step in earlier.
Right. It's like putting a mathematical structure onto this messy biological process of decay. Makes it something we can actually analyze and maybe even, manage a bit better.
That's a great way to put it. The models they talked about, the ones built using calculus, they allow for forecasting. Given the conditions, temp, humidity, how many microbes were there to start, you can use that rate, calculated through differentiation, to project when things might get critical.
Okay. So what does this all mean for us listening?
I think it really means that math, even these concepts like differentiation that might feel really abstract, stuck in a textbook, they're actually essential tools.
Yeah.
They help us tackle really critical real-world stuff like food spoilage, which ties straight into food security. Your sources just showed that beautifully analyzing the rate gives us power, the power to model, predict, hopefully cut down on waste.
It really drives home the practical application.
Yeah, and if we connect this to the bigger picture, this ability to mathematically model rates of change, it's fundamental across science, engineering, everywhere, really. It's not just food microbes. Think chemical reactions, how populations grow or shrink, even like economic trends. It's all about rates of change.
Yeah. Huh. Okay, so something for you to think about then. If differentiation lets us understand the speed of spoilage, how could knowing that specific rate help someone, say a food scientist, design better packaging, something that actually slows that specific rate down?
Good question.
Or, what other things in your daily life involve something changing over time? Could thinking about the rate of that change using these ideas give you a better handle on it? Definitely something to ponder.